Okay, in this video I'm just going to solve a couple problems related to elastic potential energy. A spring, 900 newton meters, is used to launch a projectile off a 45-degree inclined launcher. The projectile has a mass of 20 grams. If the spring is compressed by 2.4 centimeters, determine the horizontal range of the projectile. So, here's my little launcher. Here's my little mass, and I've got a little spring. It's going to get compressed, and then this thing's going to get shot. And we want to know the horizontal range. I was going to say delta x, but that's going to be confusing with a elastic potential energy. So I don't know. I'll call it h for horizontal range. Okay, so when we compress this spring, we are going to have elastic potential energy. That elastic potential energy will get converted when the spring is released into kinetic energy. That kinetic energy will give us an initial velocity. That initial velocity will allow us to predict the range of this projectile. Now, you might recognize that if that's on a 45-degree angle, it's also going to change the height of that projectile being launched. And so there should be some gravitational potential energy, but it's going to be very small, and because it's so small, we're just going to neglect it. So elastic energy is going to get converted into kinetic energy here. Elastic energy is 1/2 k delta x squared, and the kinetic energy we're going to create is 1/2 mv squared. So 1/2 900 newtons per meter. Delta x is 0.024 meters. Careful, make sure you convert that to meters. It's equal to 1/2 times the mass, 0.02 kilograms, times the velocity squared. 1/2 on both sides, so let's get rid of him. So 900 times 0.024 squared gives me 0.5184. And then 0.02 v squared, and my v works out to be square root 5.1 meters per second. So with that, effectively, I've gotten the initial launch speed of this projectile. Now I just have a simple projectile problem that we might have done when we were doing the 5 equations of motion. So in that 5.1 meters per second is on a 45-degree angle based on the launch angle. So I need to divide it into components. I can look at this one as 5.1 sine 45, and this one is 5.1 cos 45. But since it's 45, they're the same thing, so it's 3.61 in either direction. Now, with that in hand, I can divide all my information into my horizontal and vertical information. I'm going to assume this is a perfect projectile with a 0 acceleration in the horizontal direction and a negative 9.8 meters per second squared in the vertical. A change of height of 0. Again, I'm neglecting that tiny little bit that it would have moved up as it was shot. And a initial vertical velocity here of 3.61 meters per second. Using that, since I have 3, I can find time. D equals v1t plus 1/2 at squared. So 0 equals 3.61t minus, or plus 1/2 times negative 9.8 t squared. Simplify that a little bit. And I'll factor out the t. So one solution to this is t equals 0. That's not an interesting solution. That corresponds to when the projectile was launched initially. The other solution here is 3.61 equals, or minus 4.9t equals 0. Solving this one, gives me a time of flight of 0.737. With that in hand, I come up here. I have an initial speed of 3.61 seconds, or meters per second. This thing is not accelerating, so I can write out the whole equation if you want, or I could use the simplified uniform motion equation. Anyways, that whole term is 0. So 3.61 meters per second times the time of flight of 0.737 seconds. So the horizontal range is 2.66 meters. Now I kind of sped through the projectile part of this problem. If you want to see more problems on projectiles, you can go back and look at other videos. But the point is I can use elastic potential energy to find an initial speed, assuming it gets converted to kinetic energy, and then do something like a projectile problem after that. So this is my horizontal range, 2.66 meters. Alright, one more here. Determine the maximum compression in the spring as drawn. Assume no friction. So here we go. I'm going to drop this 5 kilogram object onto this spring. The 5 kilogram object is 4 meters off of the ground. The spring is 1 meter off the ground. And I'm assuming the 5 kilogram object starts with no speed. I have a spring constant. And so what I have here is some gravitational potential energy that's going to be converted into elastic potential energy. But I have to be careful here. It's not all getting converted. I'm still going to have some gravitational potential energy when this object reaches its minimum height. So my initial so I'm going to use this. Oh, that worked. Didn't seem like it did. I'm going to use this as my reference point for height for this problem. And so my initial gravitational potential energy will be mgh, where m is 5 kilograms, g is negative 9.8, and my height is 4. And my elastic energy then is going to be equal to 1/2 k delta x squared, and my final is going to be mgh2. That's my final gravitational. Now careful here, my 1/2 times 29400 times delta x squared, because I don't know how much this is going to compress delta x as this thing lands. So I have that delta x is an unknown in my final elastic energy. And my final gravitational, 5 kilograms, times 9.8. Actually, because I didn't put a negative, I don't put it there. 9.8 newtons per kilogram, times my final height. It hits the spring at 1 meter and compresses the spring by delta x. So my final height is 1 minus delta x. So my final height of 1 minus delta x goes here. And it's a quadratic and it's a little annoying, but we can solve it. So let's go ahead and do that. So 5 times 4 times 9.8 should be 196 equals 29400 divided by 2. 29400 divided by 2. 14,700 delta x squared plus 49 minus 49 delta x. I'm going to move everybody over to the left hand side here. 0 is equal to 14700 delta x squared minus 49 delta x, and then 49 minus 196. Try that again. 49 minus 196 should be 147. Yeah. Negative 147. Okay. Just looking, make sure I don't see any obvious mistakes before I enter this all into the quadratic formula. Remember, delta x is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. So in this case, I'm going to just do this all in my calculator right up front. So b squared minus 4ac square root is going to be 49 squared minus 4 times 14700 times negative 147. And then I have to square root all that. So I'm just going to punch that all in right now. So I got 2940. So negative b will be positive 49 plus or minus 2940 divided by 2 times 147. Now with the way I've written this question, I've treated delta x as a positive value. So I don't need to worry about this root. I only need the positive one. So plus 49 equals 14700. I got 0.10168 and some negative root. Again, see, when I put it in here, I called this 1 minus delta x. This delta x I've treated as if it's a positive entity. So when I did this quadratic equation, I didn't have to worry about the negative root. So here's my answer here. That's how much my spring got compressed when this gravitational potential energy got converted into some elastic energy and some gravitational energy. That kind of looks small, but remember that's 10.168 centimeters, so it's significant. And that tells you, well, that's dropping a mass on a spring, how much it gets compressed by. So there's a couple elastic potential energy questions for you to look at.